forward. Get that out of the way. If I have a function like this, domain is everything that the dependent variable can be. In other words, all possible values for x represent the domain. The range is all possible values for y. Well, am I restricted as to what kind of numbers I can plug in for x, or can I pick any number on the number line?
You can pick any number since you don't know what y is.
That's exactly right. So the domain is said to be all reals, all real numbers. In other words, there's no value of x that I can't choose. I could choose minus 100 million if I want. I could choose plus 100 million. The range, same thing. I'm going to be able to pretty much produce any kind of number I wanted to for y. There's no value of y you couldn't make. Okay? So this is a simple function. Domain's all real, range is all real. Now let me change it up just a little bit. You know what? You've worked with radical signs, right?
That's the square sign, right?
Square root, right.
Yeah.
So if y is equal to the square root of x, this function here, the domain is no longer all reals. I cannot substitute anything I want for x. It has to be a number greater than or equal to 0. So for this function, in other words, I could not put in minus 2 because I can't take the square root of a negative number. So for our domain, x would have to be greater than or equal to 0. It could be equal to 0 because you can take the square root of 0. Okay? No. So we're not allowed to put negative numbers in there. Range is similarly affected in that when you take the square root of a number, you always get a positive number. If I take the square root of 4, I get 2. There's no way I can get negative 2. Okay? In other words, I cannot produce a y that is negative. Y also has to be greater than or equal to 0. No matter what value of x I put in there, y is going to be greater than or equal to 0. Okay? Let's take a different function. Let's take this function. What do you suppose the domain is going to be on this function? What can x be? Actually, a better way to think about domain is kind of thinking in the negative. What can x not be?
0.
That's the only thing it can't be. So all reals except x can't be equal to 0. So that's the domain of this function. How about the range of this function? And kind of a way to think about the range of a function is to consider, one second, David. Sorry about that. Is to consider, is there a way to make y anything that you might want?
Well, it has to be a fraction, so less than 1.
Well, if I made x a really big number, y could get really tiny, right?
Yeah.
If I made x a million, then y is 1/millionth. So I can make y very tiny. Can I make it big? Well, what if I let x get really small? What if I divide 1 by 0.01? What does that equal to?
10?
It's 100.
Yeah.
Okay, so now if I want y to get even bigger still, I might divide it by a whole bunch of zeros in front of a 1. That's equal to like 10,000 or 100,000.
Okay.
So I can make y extremely small. I can make y extremely big. I can make y negative by making x negative. And I can make y positive by making x positive. So right offhand, it feels like I can make y anything I want. My range should be all reals. But there's one other number that y can never be.
Infinity?
0. How do you make y equal to 0? Can't do it.
Oh,
No,
yeah.
because no matter what I make x, now remember x cannot be 0, but no matter what I make x, y is never going to be 0 because this numerator is always 1. For y to be 0, this numerator has to be 0. It's the only way you can get 0. So the range would be all reals, y not equal to 0. Okay? So let me give you one more example here. What's the domain of that?
Anything but 0 minus 1.
Actually, x could be 0. You see why?
Anything but 1.
Anything but 1. So all reals, x not equal to 1. How about y? What's the range?
Same thing as x, right?
Not quite. I can have y equal to 1. So all I got to do is make x equal to 2. And y is going to be equal to 1. But what's the one thing y can't be again?
Oh, 0.
Exactly. In other words, is all we did was change the denominator, so y still can't be 0. So y is still all reals not equal to 0. So that's kind of and then one other example would be if I said y is equal to the square root of x minus 2. To figure out the domain, I would take everything that's under the radical sign and say x minus 2 has to be greater than or equal to 0. Right?
Yeah.
Which makes x has to be greater than or equal to 2. So that's the domain for this function. And again, the range for this function, the only limitation on y is it has to be positive. No matter what x is, the result of taking the square root of x minus 2 is going to be a positive number. So y merely has to be greater than or equal to 0. Okay? So you kind of getting an idea on domain and range?
Yeah.
Okay. Now let's look at their problems because they take a little slightly different approach on it. I noticed by looking at some of their problems here. If you have a table of values instead of a continuous function, let's talk about that first of all. If I have this, that's a continuous function, right?
Yeah.
Different than a table of values. If I had a table of values and I only had 4 x values and 4 y values, then I wouldn't have a continuous function. I would have 4 points. There's 1 point, there's another point, there's another point, there's another point. Now, maybe I could connect the dots and make it look like a function, but I really just have a bunch of points. So this function would not be continuous. In other words, I can't draw this without having to pick my pen up. And that's the definition of continuous. Okay.
So pretty much it can't be. Never mind. I got it.
Okay. There are some functions that are not just dots that are not continuous. In other words, I can have a piecewise function, kind of like this, that goes like that. That is a continuous function. This part of it is continuous. This part of it is continuous. But the whole thing is not continuous. It's discontinuous at the place where I have to pick up my pencil. So there's various types of functions and continuity with each. Let's see what they have to say here. Hold on. Key ideas. Notice they are, let's look up here. Here they're talking domain and range of tables instead of functions. Clearly, if we were doing it the way I just did it on paper, what would be the domain of that function without looking at the table? Remember, think as to whether there's anything that x can't be. David, you still there? Might have lost the audio. David? We lost our phone connection. How did we lose our phone connection?
Hello.
Sorry about that.
Sorry.
It took me a while to figure out that we lost our phone connection. We didn't get disconnected from GoToMeeting. We merely lost our phone connection, so I had to call back. But yeah, I wasn't quite sure what to do for a moment. Okay, let's see. We lost it in the middle of me talking, so I'm not quite sure how much of what you heard me say.
But you just moved to that segment.
Okay, this function right here, y equals minus 3x plus 4.
Yeah.
What would if we weren't basing it on this table, the domain would be all reals, and the range would be all reals. But they want us to think about it in terms of a table, a non-continuous function. In other words, the dots that they've plotted on this graph, that might not be the same one, but up here, the domain would be only from minus 2 to 2. You see why?
Not quite.
Well, because this is not really, I'm not quite sure why they've put an equation there to represent this table. It's not continuous. In other words, if I were to graph, let's do that. Here, let's graph this table. So we have x values at minus 2 minus 1, 0, 1, and 2. Our y value is going to be determined by this function here. So if I fill out this table, when x is minus 2, what is y?
So if x is minus 2, you get negative 6 plus 4, y equals minus 2.
Be careful. If x is minus 2, I have to plug it in there. So it's minus 3 times minus 2, which is plus 6.
Oh, okay, so y is 10.
Y is 10. Okay? So this value right here, minus 2 comma 10, that's 1 point. What is y when x is minus 1?
If x was minus 1, so you get,
It's okay.
y equals 7.
Okay, so at minus 1, y is 7. About when x is 0?
When x is 0, y is 4.
And when x is 1?
When x is 1, y is negative 1.
I think it's positive 1.
Oh.
Right? When I plug in 1, I get minus 3 plus 4.
Yeah, sorry.
Okay? And then when x is 2, y is...
When x is 2, y is negative 2.
Okay. So let's call that point right there.
Okay.
Hold on. Right. Come here. Okay. So I have 5 sets of points, right? And I've labeled each one of them here. So notice that the domain is the only allowable x values, which in this case are minus 2, minus 1, 0, 1, and 2. So that's the domain of this table. What is the range of this table?
So,
What's the lowest number and the highest number?
so the lowest number is negative 2, and then the highest number is 7.
Remember that first value was 10?
Oh, right.
Okay. So that whenever they give you a table and they want to know about domain and range, they want to know basically the distance. Well, the domain I could say would be minus 2 to 2, and the range I would say would be minus 2 to 10. Okay?
Okay.
Second function, this one here. What's the domain?
So for that, the domain, y can be...
No, remember the domain is referring to x.
Oh, so x can be at all reals.
Well, if you were basing it just on this, you would be correct. In other words, the way I taught you, you would be correct. But what they're kind of doing here is they're kind of teaching you domain and range 101. In other words, they're really giving you the basics, basing it on a table instead of a full function. So on this table right here, the domain is what?
The domain is all real?
0 to 4.
Oh, okay.
Just like on this other table, the domain was from minus 2 to 2. Remember, domain is only the values that... I can understand why you're confused. Part of it's my problem. I mean, part of it's my fault in that I introduced you to this concept with continuous functions as opposed to discrete tables. So we'll do it their way for the moment. Remember my way. You'll eventually need to know that. But for this particular book and chapter, they may only deal with these kind of, they may only be talking about domain and range represented by the table. Okay? They're not really talking about the domain and range represented by the function, which is what I was talking about. If we were talking about the domain and range represented by the function, both of these would be all reals for domain and all reals for range. But since we're talking about it based on the table, the domain is 0 to 4. X can only be 0 or 1 or 2 or 3 or 4. What is the range going to be?
0 to 4.
Well, when X, we got to complete this table.
Oh, okay.
In other words, we're going to need to put the Y values in for each of these values of X.
Okay, so domain, range applies to Y and
Yes.
domain applies to X?
Yes.
Okay,
so finish, let's fill this table in. So when X is 0, what is Y?
-6.
Okay. When X is 1, what is Y?
When X is 1, Y is -5.5.
Negative 5.5. Okay. When X is 2, what is Y?
When X is 2, -5.
Okay. We can see that Y is going down. So rather than fill in the whole table, let's just figure out what Y is when X is 4.
So when X is 4, Y is -4.
Okay. So I can say the range is from -6 to -4. In other words, it'll go -6, -5.5, -5, -4.5, -4. So the range of the Y values is -6 to -4. That's it. It can't be less than -6. It can't be bigger than -4.
Okay.
Okay? All right. Let's see what else they have here. I'm not a huge fan of this method of teaching domain and range, but we've got to work with what we have.
So
I'm reading their stuff here.
yeah.
Notice they say find the domain and range of the function represented by this graph. So we take the points on this graph. This is not a continuous function. It's going to be a function represented by a table. Well, that point right there is -3, -2. The next point is -1, 0, and so forth and so on. They list the 4 points. So notice what they call the domain. The domain can be -3, -1, 1, or 3. The range can be the red numbers, -2, or 0, or 2, or 4. So they don't like my terminology of -2 to 10. They want you to spell out each of the allowable inputs and each of the allowable outputs. That's what they're calling domain and range on these non-continuous functions. Okay? So, let's see. Can you read this good enough? Hold on a second. Let's see if I can figure out how to make this bigger. How do I make this bigger? Well, let me go down down some more. I'm not sure you can read this graph closely enough to tell me what the, well, I don't know, can you? What's the domain on this one I'm pointing to here?
-3, -1, 1, and 3.
Good. What's the range?
The range is -1.5.
No. What's the y value on that point right there?
Oh, sorry, I could not see that. My bad. -3.
And again, this point here?
-3.
And -3 and -3. So the range is -3. That's it. No matter what x is, y is -3. All right, so you know how to do those. Hold on, let me. Yeah, they're going to stay on these tables the whole way here. Number 12. I know you know how to do 9, 10, and 11, right?
Yeah.
What's the range on 9? I'm sorry, what's the domain on 9?
-1, 0, 1, and 2.
Okay. On 12, what's the domain represented by the table?
1, 2, and 3.
What's the range?
6,850.
Yeah.
7,953.
Those numbers, yeah, whatever those numbers are, right. I think that's a point, not a comma, but that's okay. Okay, now we get some interesting functions down below. These are no longer based on tables. These are based on number 14. Y equals absolute value of x. You've had absolute value, right?
Yeah.
Okay. Now we're talking what I was talking about in the beginning. Let's do that. Now we're talking about a continuous function. And I'm going to graph this function. And of course it goes to infinity in both directions. What's the domain of this function? Read it from the graph. Yeah, all reals, right? Is that what you said? All reals?
Yeah.
Yeah, in other words, x can be anything. There's nothing that x can't be. X can be 0, it can be 1, 2, it can be 100 million, it can be minus 100 million. What's the range?
The range is also anything.
Look at the graph. Can y be negative?
No.
Range is y is greater than or equal to 0. In other words, you can frequently read the domain and range of a graph directly without doing it algebraically. In other words, we could contemplate this function and realize that this is the domain and range. But we can also read it directly from the graph. Let's go back and graph this one here. It was one of the first ones I put up. If I graph this function, I don't know if you know what it looks like, but it's a hyperbola that looks like this. The hyperbola is never going to hit the x-axis, and it's never going to touch the y-axis. It's going to approach them. I don't know if you've ever talked about this function or not, the hyperbolic function.
No.
Okay. Remember when we did it algebraically, the domain was all reals except x could not be equal to 0, right? It turned out the range was pretty much the same thing. All reals, y couldn't be equal to 0. Well, if you look at that function, if you look at my graph here, you would be able to get this information by the graph. In other words, the x values, they come all the way from negative infinity, right?
Yeah.
And they go all the way up almost to 0, but they don't quite ever touch 0. Then they skip the 0, and you could have x be 0.00001, and then it'll go all the way up to positive infinity. So you can see from this graph that x never crosses the y-axis, never touches the y-axis. So x is never equal to 0.
Yeah.
And I could get that information by just looking at this graph. Likewise, if I want to know what y can be, well, y comes all the way from negative infinity, comes all the way up, almost hits the x-axis, but never really touches it, just approaches it. And on the other side, it goes all the way to plus infinity, and it comes awful close to 0, but it never is 0 either. So according to this graph, the domain and range fit this definition perfectly. All reals except x equal to 0, and y can never be equal to 0.
Yeah.
And when I had the x minus 1, that's also hyperbolic, but you know what an asymptote is? Have you ever heard the expression asymptote? It's a line that the function never touches. In other words, if I graph 1 over x minus 1, it graphs like this. And again, if we look at this, we can see that x has all values except 1. It never crosses the vertical line x equal 1. So I could read the range being all reals except x equal 1. I'm sorry, the domain. And when I look at the range, well, it does the same thing. It comes up, it tries to touch the x-axis, but it never touches it, and it jumps on the other side. So the range stays at all reals, y not being equal to 0. So just so you know that you can figure out domain and range from a table of values, like they did in the book, or algebraically from a function by analyzing a function, or graphically by looking at the graph of that function. All three of those ways will give us domain and range. Okay? Let me give you another one I'm going to make up. Y equals, well, y equals square root of x looks like this. See how we get the domain?
Yeah.
By looking at the graph, we can see that x never gets negative. It's only positive. It goes everywhere from 0 to infinity. Same thing with y. If we look at the range by reading it from the graph, this actually goes all the way up to positive infinity eventually, but it never is negative. It never is anywhere down here. So from the graph, we would be able to get the domain and the range.
Okay.
And let's look at this other one here. How about y equals negative absolute value of x? And since you're not that familiar with absolute value, I'll graph that for you. That's what the graph is. What's the domain?
So the domain of negative absolute value of x is anything.
Good. What's the range?
And then the range anything negative.
Right. In other words, the range is y has to be less than or equal to 0. And we get that from the graph. We also get it from the fact that we know this is always going to be positive. So if you stick a negative sign in front of a positive number, you're going to have a negative number. Y equal absolute value of x minus 6. Y equal absolute value of x minus 6. Well, let's try to figure out what that might be without graphing it first. Domain?
So x can be anything but 6.
It actually can be, it can be 6. X can be anything. I have no restrictions as to what I can plug in here. I can plug in 0, I can plug in fractions, I can plug in negative numbers, positive numbers. Okay?
Oh.
So domain is all reals. In other words, I'm not restricted. When you think about domain, the first question you always want to consider is what can it not be? Well, it can't be, there's nothing it can't be. Okay, but now let's look at range.
Oh.
Since this has to be positive, what is
So
what's the smallest value that y could be?
negative 6.
Very good. So y has to be greater than or equal to negative 6. And if I graph this, well, it's the absolute value function shifted down by 6 units. In other words, this represents a vertical shift down of the curve by 6. So I'm going to graph it like that. Absolute value graphs always have this big V. And from this graph, you can see what the domain is and the range is. You can see that y has to be bigger than that minus 6 right there. But it could be equal to minus 6. In other words, if you let x be 0, y is equal to minus 6. So that's part of its range. And the last one they have is minus the absolute value of x, here, let me, plus 4. Let me erase this. So minus absolute value of x plus 4. Now they're getting kind of tricky on us on the range. Domain, what's the domain?
For that equation?
For this function,
So,
yes.
yeah, could it be anything again?
Yep. Range.
Anything above negative 4.
Well, let's think about it here. Anything above negative 4? No.
Well, any reals?
Let's plug in some numbers just so I can demonstrate. When x is 0, what is y?
4. Oh, above 4.
Okay, so there's a point on our curve. When x is 4, what is y?
8.
What is, when I plug in 4 for x, then I take the absolute value of 4, which is 4, and I put the minus sign in front of it, I get minus 4 plus 4. So when x is 4, y is 0.
Yeah.
So that point's on the curve. When x is minus 4, what's y?
So when x is minus 4, it is 8.
No? In other words, we're going to do this. Okay, remember we're dealing with the absolute value function. I know you don't have a lot of experience with it, so I get why you're having trouble with it. But do the absolute value first. When you take the absolute value of minus 4, you get 4. So that is equal to minus 4. So
y equals 0.
Yeah. And again, we have this function that looks like an upside down V. So what's the range?
The range is anything below 4.
Less than or equal to positive 4. Okay? That was a little harder to figure algebraically. But if I knew how to graph that, I would have instantly figured out the range, right?
Yeah.
So kind of remember that. If you have trouble figuring out the range and domain, graph a few points, and if you have a basic idea of what this absolute value function looks like, you'll be able to come up with the range easily. Range is always the hard one to come up with. Domain is never hard. I mean, domain is particularly easy to come up with. Range, not so. Range is always the hard one to figure out. See what else they've got here in the fair game review. Graph the linear equation. You know how to do that, don't you? 15. Start at 8, make a slope of 2, and connect the points. How would you graph 16?
So to graph 16, it would be 5x plus y minus 12. So, is that an equal sign?
Yes, it is, actually. Yeah, these are all equal signs here.
I know you can do it the other way, but I feel like it's easier.
There's two ways to graph it.
Yeah.
There's putting it into y equal mx plus b format.
Yeah.
Let's do that.
That's my easier way.
Okay. Well, that's actually the harder way, but I'll show you the easier way. So let's do it the hard way. So what's the next line I'm going to write?
Y plus 5x plus, xy equals 5x plus 12.
Okay. If we're trying to get it into y equals mx plus b format,
so if we want to
I want to solve for y, right?
Yeah.
So solve that equation for y. What's the first thing you're going to do?
You're going to divide.
Not quite. Let's get this 5x on the other side.
What was that?
Let's move the 5x to the other side. We're trying to isolate the y, so we want to get rid of anything that's not y. In other words, if this 5x term needs to be moved to the other side, if I'm going to eventually get this thing into that format. So the first thing I would do would move the 5x over.
Yeah, I'm really sorry. You're coming through really, really choppy.
Okay. Yeah, I don't know what to do about that. But next, what would I do?
What you want to do in that case? So you have by.
Actually, that's 6y. Yeah, I'm sorry. This is a b over here, but this is a 6.
What you would want to do is simplify the equation.
Well, you want to solve for y. How do we solve for y?
Oh, okay. So to solve for y, it's already, so y equals, you divide by 6 on both sides.
Okay, there you go. So minus 5, 6x plus 2. Now we have it in y equals mx plus b format, and I can graph it. Where do I start my graph?
So you start your graph at +2.
Okay, right there.
And then you go to -5/6x.
Well, I need a slope of -5/6. Okay, so I got to go up 5 over 6. 1, 2, 3, 4, 5 over 6 that way, because I want this slope to be negative, right?
Yeah.
Okay. So that was one way to graph it. There's actually a far easier way to graph it when they give it to you in this format. Let me show you what it is. I'm actually going to graph it on a different piece of coordinate plane. Notice that my y-intercept is always the place where x is equal to 0. You get that?
Yeah.
So if I plug in x of 0 here and solve for y, I have my y-intercept immediately. Y equals 2. That point's on my curve. That's my y-intercept. Well, if I knew what the x-intercept was, I could plot this thing without even figuring out what slope is. Well, the x-intercept occurs when what is 0?
When y is 0.
Exactly. So I plug in 0 for y and I solve for x. X is equal to 12 divided by 5. So this point here is 12 divided by 5, and this point here is 2. I've got 2 points. Any 2 points determine a graph, a linear equation. Looks exactly the same. Has the same slopes, the same line, goes through the same points. But I didn't have to put it into y equal mx plus b format. Is all I had to know is that the x-intercept is where y equals 0, and the y-intercept is where x equals 0. And once you get your 2 intercepts, well, now you just connect those 2 dots, and that's your line, as long as we're dealing with a linear equation. Notice that these all say graph the linear equation. What is a nonlinear equation? Y equals x squared is a nonlinear equation. That is a, yeah, it doesn't make a straight line, and that's a curved line. That's a parabola. So linear equations always are straight lines. And straight lines are always determined by 2 points. You only need 2 points. So it doesn't matter if I get 1 point and slope, or 2 points, like I did the other way. All right, let's see. So you know how to graph all of these. "19. The minimum number of people needed for a group rate at an amusement park is 8. Which inequality represents the number of people needed to get the group rate?" A, B, C, or D?
Sorry.
It's all right.
I need to enlarge the screen really quick.
Okay.
Kind of small right now.
Here, let me do it.
Okay.
That help any?
Thank you.
Yeah.
Okay.
So the way to answer this is, let's look at each answer and see if it makes any sense. Are they saying you have to have less than or equal to 8 people?
You need the minimum.
Yes.
You,
Yeah, in other words, if you're going with a family, it better be 8 people in there if you want the group rate. If you only have 7, you're not going to get the group rate. So which answer are they looking for here?
E.
Yeah.
Because they want to have something less than or equal to.
Greater than or equal to.
I mean, yeah,
Yes.
that's
Yes. Yes. Okay. Good. Well, we covered a lot of stuff today. New stuff for you. Domain and range was completely new, right?
Yeah.
Yeah. Domain and range actually is going to be pretty important by the time you get to Algebra 2. So they're just kind of introducing it here in Algebra 1. And then, of course, it becomes even more important in higher maths, calculus, and stuff like that. So you're definitely going to need to know about domain and range. I'm glad we covered it. But I don't know that I want to go beyond that. I think we should not try to cover too many different topics in one session that are new to you. If we were reviewing, I wouldn't care, but I don't want to overwhelm you with new stuff, the meaning of new things. What is the independent variable in a typical equation like this? In y equal absolute value of x, what's the independent variable? What's the dependent variable?
Y is dependent.
Good.
And then x is independent.
Okay, so the domain goes with the independent variable. Range is the dependent variable.
Okay.
All right. Yeah, that's all in that chapter. So why don't we end it with the new stuff for today, and we can pick up we'll go from here next time. What are you doing in your class? What kind of stuff?
Right now, I think since it's getting close to the end of the trimester, she's just kind of bored because, so we're just doing like volume, surface area, and geometry.
Okay.
It's really
That's actually pretty good. That's pretty hard stuff. In other words, that's second semester geometry.
Yeah, no variables are involved.
Oh, really? Okay. So
Yeah.
you're not doing like the volume of a sphere?
No.
Which is 4/3 pi r cubed.
No. I know cylinders, though.
Okay. When you have the volume of a cylinder, it's what?
Pi r squared times height.
Yeah. Whenever you have an object that is uniform from bottom to top, then the volume is always going to be the area of the base times the height.
Yeah.
It doesn't matter if it's a cylinder or a brick. In other words, a rectangular block. If I said a rectangular brick, this is a three-dimensional solid, which I'm not very good at drawing, but something like that. Same concept. To find the volume of this, we know it's the 3 dimensions times each other. In other words, it's base times depth times height. But it also is true that it's the base, the area of the base, times the height.
Yeah.
So volume, always keep that in mind about volume, that if you can get the area of the base and it's uniform all the way up, then it's that. So let's talk about a cone. A cone isn't uniform all the way up. When you go to a point, you are shaving off 2/3 of the volume. So to remember what the volume of a cone is, it's the same as the volume of a right cylinder, only it's only 1/3 of it. It's 1/3 pi r squared times h. David, do you mind if we end early? I have a client at my door.
Yeah.
Okay. I will talk to you next time. Bye-bye. on down. We'll sit and chat for a little bit. Light on the subject here. Hi. Hi. Come here. Come on.
Do you know Miss Eggleston?
I don't.
Okay.
I don't know too many of the teachers, but I do have. Okay.
That works for me.
That's right. Yeah.
That works.
Yeah, it's always easier if I have the textbook.
Yeah.
So you go to Chatfield, and you're a junior?
Yes.
Okay.
So my ACT this year, I gotta really try.
When are you taking the ACT?
So we have spring break, and then it's the week after that, so
It's after
January,
spring break.
February, March, April, so April.
Okay.
April 8th, probably.
Okay. Quite a few students on ACT, especially people taking algebra too, because most of them are taking the ACT.
Yeah, and it's hard.
Yeah, so I've done a lot of work with ACT. You found me by counselor's office?
I found you by the Ken Carl.
Oh, the ad in Ken. Yeah. I don't know if you had a chance to go to my website.
I did. I had a chance to briefly glance at it. Yeah.
Okay.
Yeah.
You don't really need that if you've been to the website. That's just a printout of
Yeah,
the
that's
website, pretty much. I apologize for the smell in here. I had a little bit of a water accident. I woke up this morning and my carpets were flooded.
Oh no.
Yeah, so there's a bit of a musty. I'm trying to air it out all day.
Yeah. Was it a broken pipe?
No, thank goodness. Although I'm not sure what the fix is. I think the tank leaked.
Water tank?
Yeah, because
Okay.
it was half empty.
Yeah.
The water, and somehow the water's leaked out of that water tank. We've got to get the plumber in here tomorrow and fix it.
Look at that. Milestones of mathematics. That's not many people have that poster on their wall.
Yeah, that's a good one. Yeah, that's a really good one. That's the mathematicians from 1500 through 2000. I actually have another one, their office in there, that goes from BC up to 1500. They break it in two.
Wow.
And that poster is more.
And your math clock? Boy, you're a math
Yeah,
guy,
this is my math room for sure.
Wow.
It's,
That's nice.
I see some students here. In general, I do most of my tutoring online.
Okay.
And if that's something you want to consider, it might be easier for you, it might be preferable. There are some advantages to the online.
I did online school my sophomore year, and that's why I really feel like I've lost so much. Like, I used to be so good at math, and then as soon as I missed that semester, it was geometry, so it just like really messed me up. And then did summer school, and I went back to Chatfield because online school was too hard for me, and like I couldn't handle not seeing my teacher and not having hands-on.
Excuse me a moment, I hear this beeping here. I realize I'm running this GoToMeeting session.